Hello everybody, we're getting ready to do lesson chapter 8, review and summary for pre-calculus math today, part 1. And for today's lesson, you got 0 points in your notebook and you got 70 points in your class worksheet. Name, date, period in my classroom. Due date for homeschoolers and onliners. And then for today's spell work, determine whether the statement is true or false. Justify your answer. For 97, 98 students, teachers, justify your answer. So give your students about 5 minutes, 6 minutes for this, teachers. See you in 6 minutes. Okay, welcome back for the solutions for today's bell work. True or false? So we have n plus 2 factorial over n factorial. Does that equal n plus 2 multiplied by n plus 1? Is the question up here for 97. And it is true because n plus 2 factorial over n factorial would be the same thing as n plus 2 multiplied by n plus 1 factorial, n factorial over n factorial. These cancel and then you're left with this, so it is true. And then for this summation down here, true by the properties of sum, you can move this over here and it's an equal statement here for that one. Into our lesson for chapter 8, review and summary, and we go right into our first section here in chapter 8, 8.1, sequences and series. Use sequence notation to write the terms of sequences. So an example of that would be these down here. These will be sequences here. So a to the n would be 7n minus 4. So these are all examples here of a sequence down here. And then another part that we covered in 8.1 is use factorial notation. If n is a positive integer, then n factorial would equal 1 times 2 times 3 times 4, blah, 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 times n minus 1 times n. So this would be your abstract representation of factorial notation. Remember that, students, from 8.1. And then use summation notation to write sums. So to do that, the sum of the first n terms of a sequence is represented by this symbol here, your summation symbol, n as your upper limit, and then you start down here at I equals 1, and then you start here a to the I, and then you continue here with your sequence here for n terms. And then find sums of an infinite series. So an example of that would be here. So the sums of an infinite series, infinity will be your top limit, and then I would equal 1 here. So you start with 1 here and you go out here to infinity, and then when you add these it approaches 0.5555, which when you fractionate it will be 5 over 9. And then for here, use sequences and series to model and solve real life problems. Remember that. And then an example of that, it can be used to model the resident population of the United States from 1980 through 2008. And there is an example, example 10 illustrates that further. And then we go into a guided practice here. Find A, the fourth partial sum of this summation here, and then B would be the sum of the infinite series. So for this one here, the fourth partial sum of, you have an upper limit here of infinity, and then you start here, k equals 1 here, 2 times the quantity 0.5 to the k power. And then when we find that partial sum here up through 4, we go up through 4, and then that would equal 1.875. And when you fractionate that, you have this fraction for that. And then B, the sum of the infinite series of this. So the infinite series here, using our formula for that, we have 2 times 0.5 to the k power. And 2.0.5 multiplied by 1 over 1 minus 0.5 would equal 2. So it eventually comes out to 2 for the infinite series of that. Okay, moving on now into our next section of Chapter 8. And for 8.2 section, arithmetic sequences and partial sums. So recognize, write, and find the nth term of an arithmetic sequence. So to do that, an example of that would be here. A to the n would be, for example, 9n plus 5. And then we put in here our different terms and we come out with different sums of these sequences. And then find the nth partial sum of arithmetic sequences. So an example of that, the sum of a finite arithmetic sequence with n terms, for example, will be s to the n will be n over 2 multiplied by a to the first plus a to the nth. So remember that formula from 8.2. And then another part of 8.2, use arithmetic sequences to model and solve real life problems. An example of that, arithmetic sequence can be used to find the total sales of a small business, and that will be example 7, will be in this problem set here. We've done that before, so that's what we covered in 8.2. Okay, for our guided practice here, the starting salary for an accountant is $36,000 with a guaranteed salary increase of $2,250 per year. A, determine the salary during the 5th year, and B, down here for you students, the total compensation through 5 full years of employment, total compensation down here. So for A here, determine the salary during the 5th year. What would the 5th year salary be with 36,000 start and 2,250 increase per year? This would be your plug-in here, 36,000 plus n minus 1, 2,250. You plug in your value, 5 minus 1, and you get 36,000 plus 4 times 2,250, and you end up with $45,000. Okay, onward into our next section here, section 8.3, geometric sequences and series. Recognize, write, and find the nth terms of a geometric sequences. So for that, here's an example here. Remember, a to the n equals 3 times 4 to the n. That'd be an example. And then you plug in your values and you come up with your final result from your nth terms of geometric sequences. Find the nth partial sums of geometric sequences. So geometric sequences for that. This is your formula here, a1 times r to the n minus 1, with your common ratio cannot equal 1, and then this would be a way that you would find the sum of that, would be using a summation, upper limit of n, and then your initial would be at 1 here for that. And then this would be your formula finally for finding the nth term down here, n. So it'll be a to the first times quantity 1 minus r to the nth over 1 minus r. That'd be how you would find your nth partial sum of a geometric sequence. And then find sums of an infinite geometric series. And then this would be your formula here. So for the infinite here, and then this would be your sequence here. Then you again use a summation where the upper limit is infinite, and you start with the 0, a1 r to the I, and then you would end up with this formula here, a1 over 1 minus r for that one. And then finally for 8.3, use geometric sequences to model and solve real life problems. And then we see example 8, so remember example 8 from 8.3 would have that. So if you have your class worksheet, you can go back to that to see an example of a real-life problem. So let's go into our guided practice now for 8.3. Find the sum, use a graphing calculator to verify your result. So we have an upper limit here of 7. We have an initial starting place here for 1. And here is our geometric sequence, 2 to the I minus 1. And then down here, since this is yours. But for up here, the solution for that, we have this sequence here, and we go up through 7 here, our upper limit. And then for that, we would have 2 to the I minus 1. And we have 1 minus 2 to the 7th over 1 minus 2. And then to find that, to find the sum of 7 up through 7 sums, up through our 7th entry on that geometric sequence, it'd be 127. And then finally, let's go, not finally, but let's go on to 8.4 now. The binomial theorem. Use the binomial theorem to calculate binomial coefficients. So this will be an example of that. And again, your formulas down here are key. N choose R, n factorial over n minus r factorial multiplied by r factorial. This would be your formula for that, to calculate binomial coefficients. And then, so this would be an example here of the expansion using a binomial theorem. And by using that, you would figure out your coefficients. And then use binomial coefficients to write binomial expansions. So for that one here, this would be that. And then your coefficients are down here for x minus 1 to the 4th. And you can go back into your triangle, and then this would be your coefficients here for the third row on the triangle to come up with your coefficients. And then use Pascal's triangle to calculate binomial coefficients. That could be that one there, but this is your Pascal's triangle here. And you could use this on this one for sure. So that is 8.4. Then let's try one here. Find a binomial coefficient. So use a graphing calculator to verify your results. So we have 10, choose 8. This is yours down here. So for this one here, 10, choose 8, you would come up with this here. Here's your formula. For that one, and you come up with 45 for your amount here, your count result from 10, choose 8. Okay, moving on now into 8.5 for Chapter 8, Review and Summary. 8.5, Counting Principles, solve simple counting problems. So for that, remember, a computer, this will be a problem that would qualify as a simple counting problem. A computer randomly generates an integer from 1 through 15. A computer can generate an integer that is divisible by 3 in 5 ways. So 3, 6, 9, 12, and 15. That would be an example of a simple counting problem. And then using the fundamental counting principle to solve more complicated counting problems. So an example of that would be let E1 and E2 be two events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can occur in M2 different ways. The number of ways that the two events can occur is M1 times M2. So that would be an example of a little bit more complicated counting problem than the first one. And then use permutations to solve counting problems. Again, we'll use permutations now. And a permutation, the formula for that would be NPR. So it would be n factorial over n minus r factorial, instead of the combination where you have another product out here. You just have this formula here, and let's see, in other words, there are n factorial different ways that n elements can be ordered. So it's just an order, special orders, or permutations. And then use combinations to solve counting problems. So for that one, we have NCR, which would equal, see, we have this extra factor out here where it makes combinations would be a smaller amount because of this extra factor that you multiply your initial denominator by. You multiply again by R out here, and it makes the total combinations a smaller number than the permutations would be. Let's do an example here. Solve for n. For this one here, n plus 1 time n plus 1 p2 equals 4 times np1. So we have an equation here to solve. Same thing for you down here, students. So for this one up here, n plus 1 p2 equals 4 times np1. So for this one over here, this would be the same as having n plus 1 factorial over n minus 1 factorial. And then it would equal 4 times n factorial over n minus 1 factorial. Again, using our original formula for finding permutations. And then when we multiply this over here, this will cancel here, and you'll end up with n plus 1 factorial equals 4 times n factorial. And then finally, solving for this, you'll come up with n equals 3. So let's see, n would equal 3 here. N plus 1 factorial divides through, see, and then move this one over here, and then you would get n equals 3. So we did plenty of homework to perform that skill. And then finally into 8.6, probability. Find probabilities of events. So this would be an example here of a probability event would be n over e, or rather n of e over n of s. Event e has equally likely outcomes, and its sample space s has ns equally likely outcomes. Then the probability of event e would be this. And then find probabilities of mutually exclusive events. So mutual exclusivity, this would be your formula here for mutually exclusive events. So probability of A union B would be probability of A plus probability of B minus probability of A intersecting B. If A and B are mutually exclusive, then this would be your final formula here for that. Up here, if A and B are events in the same sample space, then probability of A or B occurring is this. And then down here, if they're mutually exclusive, this would be your formula here, probability of A plus probability of B. And then find probabilities of independent events. So that would be, independent would be probability A and B. You just multiply them together, and then that would be your probability of both events happening. And then we can try one here. We have this table, a sample of college students, faculty members, and administrators were asked whether they favored a proposed increase in the annual activity fee to enhance student life on campus. The results of the study are shown in the table. So we have favor, oppose, and then total here for students, total faculty, total administrators, and then our total here that favor, oppose, and then our grand total down here of people here, 500 people. A person is selected at random from the sample. Find each probability. The person is not in favor of the proposal, so oppose here. So the person, so how many have we got in opposition? Would be 208. So to find that, amount, you would just divide 500 into 208 and you come up with this percentage here for A. And then this is your students down here, person and student, and the person is a faculty member and is in favor of the proposal. So that is yours. And that is 8.6. Chapter 8, not 8.6, but that is Chapter 8, Review and Summary, Part 1, Pre-Calculus Math. If you need class worksheets and the homework sheets and solution PowerPoints or any other course material, email me at animatedpowerpointmathvideo@aol.com. Thank you.